Mamba and related works, as well as comparing these things to transformers, which I think everyone should be familiar with. This is based on a past series of talks I've given that I also turned into a blog post. So if you've seen those, there's not going to be too much new, but hopefully this is new for at least a sizable portion of the class. Um, so I'll get right into it. So many of you have probably heard of Mamba, which is a state space model. Probably everyone is familiar with transformers, I hope. Transformers were the dominant model for sequence modeling for many, many years until around when Mamba came out in late 2023, 2024. And since then, there's been a large resurgence of all sorts of different models. Um, some of the ones that I've shown here that you might have heard of include things like XLSTM, um, more recent paradigms like test time training. There is this RWKV series, although that's fallen off a little bit. Maybe you've heard more of the DeltaNet family and the follow-ups gated DeltaNet. All of these are related models, and they can all be classified as recurrent models or linear models, is what many people call them. Some people call them linear attention. Some people just call them like linear sequence models. Some people call them, RNNs. All of them are in related families to state space models and Mamba as well. And what I'll talk about here, actually, I want to be a little more broad than just Mamba and talk about a lot of these in general, rather than making it specifically about Mamba. I'm going to focus on the autoregressive modeling settings. All of you should hopefully be familiar with this. So, the setting where you're predicting the next token probabilities given in a sequence, conditional probabilities, and then you can generate tokens one by one at inference time. This applies not just to language modeling like the GBT series, but any sort of sequential data. And um, I'm not going to define a lot of these models very technically, but um, I guess I'll just show just so we're on the same page, kind of what we should know about attention. So the way I think about attention is not the whole QKV thing, but I think we'll think about it just in terms of what these models do at inference time. So um, so a transformer, what it does is if you give it a prompt and you ask it to generate the next token, it does this thing where it compares this token to all the previous tokens. Um, so this is where the pairwise comparison comes from in attention. But instead of thinking about the QKV stuff, we can just think of it abstractly as doing all these comparisons, and then it uses that to figure out the next token. And then in autoregressive generation, you just keep adding that basically to your context or your prompt. You keep guessing the next token by comparing all previous tokens. And this is what leads to the quadratic complexity, right? The main point, though, is um, what attention does and how you should think about it is that attention is the de facto model that tries to attend over its entire history all the time. And in order to attend over its history, it needs to cache its entire history. So basically, attention is characterized by caching its history. If you know more about the actual implementation and systems of transformers, we call this the KV cache because of the exact way it's defined. This is it's probably its main bottleneck at inference time. A lot of work on transformers is how do you optimize the KV cache and so on and so forth. But in a nutshell, we just think of the transformer as being characterized by this caching mechanism. Um, and so this kind of defines its all of its trade-offs. So because of this cache, at inference time, the amount of memory you have to store keeps increasing. The amount of computation you have to do keeps increasing. This is also what leads to the so-called quadratic problem for attention. When you amortize this over an entire sequence, it goes from linear to quadratic, um, and so on. And so this is basically the defining feature of a transformer. Um, and so when you go over the entire sequence, when you sum over the entire sequence, this is quadratic. And then high level in state space models and in all sorts of linear models, we think of them instead as linear time models, where so linear is over the whole sequence length again because every step is constant. Because the defining feature is that instead of caching the sequence, no matter what prompt you get, you kind of stream them into the state space model. They get compressed into a fixed size memory, denoted by this blue ball here. And then this memory is constantly evolving as you keep generating more data and seeing more data. So you never store the past data exactly. You always are compressing it. Um, and so this is kind of the high level trade-off of a description of a status model. So I'll go a little bit into more detail about how do I think about SSMs and these other linear models now. But this is kind of, the high level view. So so if you like actually read the Mamba paper and any of the follow-ups, they're highly technical. You have to define the models quite carefully. And you have to think a lot about how do you compute the models, how do you, initialize the models. Um, but I think that a lot of them can be abstracted out into just very core high-level concepts. That is what made them work. So yeah, so we can think of these as well as kind of like ways in which these models have differed from traditional RNNs. So I kind of think of SSMs and other things like linear attention, basically as the modern RNNs. And these ingredients are the ways in which all of them differ from the classical RNNs. And here is kind of the formula that we usually use for these models. So all of these linear models generally can be written in this form, including, your gated delta nets and your other models. They all have this form where you think of it as taking an input x that's unbound over time. You have an input matrix that converts this into a form suitable for the hidden state. Generally, this blows up the state dimension. And then you have a linear transformation of your previous hidden state. You incorporate your current information, and that becomes your new hidden state, right? So basically, there's this recurrent update where you're constantly updating the hidden state. Um, and then projecting that out. So this is basically like a recurrent neural network. How do they differ? So the first ingredient is that the state size is much bigger than a traditional RNN. What is the state size? That's basically the size of this H of T, right? The hidden state. Why is that? Because the state size basically defines how much information can your model remember. Because the hidden state is what summarizes all of the context. In the previous, picture, when you take in data and then you put it into the state, um, this blue is the hidden state, and the size of that basically is how much information is your model remembering. And so, in all of these models, they try to remember much more information than um, traditional RNNs. I call this state expansion. This has other terminology that other people call it, and what this means is that if you have a one-dimensional input sequence, like if x is one-dimensional, the hidden state will be n-dimensional, where n is on the order of like 100. So you're kind of blowing up the information by a factor of 100. And so your hidden state is going to be 100 times larger than that of like an LSTM and a traditional RNNs. Um, Again, this all of these ingredients also have been used in various shapes and forms that are listed down here. So um, linear attention was maybe an earlier model that had something akin to state expansion, as well as other models. The second key ingredient is the expressivity of your state update function. So you can basically think of any RNN as being defined by a hidden state update function, right? So there's a black box function that takes in the previous hidden state and the current input and turns that into the next hidden state. Um, in this case, this black box function is this linear combination. And in general, the expressivity of this is governed by many things. But that expressivity is what allows the model to control what information is being stored in the state. The more expressive this update function, the more control the model has over what is in the hidden state. And so in modern linear models, this is controlled by a few things. So what Mamba introduces what we called selectivity. This is essentially a the same concept as gating in traditional RNNs. So LSTM's GRUs introduces this concept called gating. Selectivity is basically the same thing. In the context of Mamba, what this means is that these transition matrices ABC in the older style of SSMs, which I'm not going to go over, but these used to be constants, constant parameters. And in Mamba, they are instead data dependent matrices. And so this is what allows the model to select specific information that it wants to pay attention to. More modern recurrent models like gated delta net and later, They are all have the same form here, but what they do is they control these matrices to be even more expressive. So the toggle that a lot of people do is that this A matrix, which is the biggest factor in determining the dynamics of your recurrence, you can make this more expressive by choosing the structure that it has. Because all of these models are also very structured. So Mamba chooses a diagonal A matrix, and then later models can choose more expressive versions. But the key ingredient is that all of these need to be data dependent, which we call selectivity. And this allows the update function to be much more expressive. And so combined with a larger state and a more expressive update function, this allows the model to be much more powerful. And then finally, with a larger state and a more expressive state update function, your model is more powerful. The trade-off is always that your model becomes harder to compute and much slower. And so the final ingredient is how fast can you compute the model during training? Um, and so in Mamba, what we did is a technique called associative scan. Basically, it's a technique for computing linear recurrences like this. And um, it basically allows you to parallelize this recurrence in a way that is much more efficient on modern hardware so that you don't have to compute the recurrence one step at a time, which is the de facto way of computing recurrences like in LSTMs. Um, there's even more advanced ways of computing this faster by rewriting it as a mapmol, which I'll touch on in a second. But yeah, and again, like these techniques have all been done before. Um, but it's critical to getting the models to work at scale. And so Mamba, the way I think of it is that it's really basically the first model that combined all of these ingredients into one model. All of these ingredients have been used before in isolated settings. Um, but when you put them all together, then you get a model that is, you get basically a recurrent model that is still linear time, like older RNNs, but they're much more expressive because of a larger state and a more expressive state update function. And because of the linearity of this recurrence and clever techniques for computing them, they're much more scalable than things like LSTMs. And so the combination of all of these showed that recurrent models can be competitive with transformers across the board on many data modalities, even on language modeling, but especially on other modalities, which I will touch on later in this talk. Um, yeah, and so that's why, these models became really, the community got really interested in them. I'll say a little bit more about okay, so after Mamba came out, there's tons and tons of related models that were published. This is a table from I think the DeltaNet paper that kind of shows the difference between all these models in terms of their update rules. Um, and I think that actually I think that all these models are more similar than they're different. You can keep tweaking the models and making them, either faster or more expressive or whatnot. But I think that they all have similar trade-offs. And the most important ingredient is efficiency. And so I'll say just a little bit about efficiency, especially given that this is, a class about systems. Um, in Mamba 1, um, I didn't really talk about it, but basically there needs to be really clever tricks to get the model to be computed fast. So let me go back a few slides. Um, So we can think of Mamba 1 as um, this linear recurrence. It's computed using a technique called associative scan, which I won't go into the details of. Um, and then there's the state expansion, so that like if you have like a 1,000 dimensional input, like these are very similar to transformers in terms of the way the model is constructed, right? So if you have a D model or a model dimension of 1,000, the hidden state is going to be dimension 1,000 times 100, and that's way too big to materialize. So Mamba 1 uses the kind of this clever systems trick, which was introduced in earlier hardware-aware models like flash attention, um, where it basically only materializes certain parts of the computation in more efficient levels of your memory hierarchy in your hardware. So GPUs have this main memory HBM, and then it has these faster memory like shared memory SRAM that the registers share, and other like faster caches like the L2 cache and so on. Um, and then so the idea here is that your GPU has a heavy memory bottleneck when you're transferring things in and out of memory. Um, if you heard the terms compute bound, memory bound, that all refers to basically storing things in the HBM. And so what Mum1 does is that even though the state is super large, it never materializes the state in HBM because that would incur tremendous memory costs, memory bandwidth transfer costs. Um, and instead, when it does materialize the state, but it only does this in SRAM. And so what you'll kind of do is like you'll transfer your input into from main memory into SRAM. Um, so here's like your input X. You hit it with your state expansion vector, which is also in main memory, but you basically transfer these into SRAM and do the state expansion in SRAM, which is in orange here. Then your larger materialized state is only being processed in SRAM, and you do the entire SSM recurrence in SRAM, and then you project it back out um, uh, to the output in back into main memory. So this basically used this kind of clever trick of controlling exactly where your computation is done, and this was what made this state expansion type family of models actually feasible to compute. Um, Later versions have moved away from this. This Mamba 1 almost brute forced this problem. Later versions have used much more clever math to figure out other ways to make computation much faster. So Mamba 2, as well as many, many other types of models like all the delta nets and so on, they all use clever tricks to figure out how to compute the whole recurrence by transforming the equation into matrix multiplications. So they all do this thing where you kind of chunk the sequence into these windows of length like 128 or something, and then computing the entire input to output map within a window. Instead of expanding the state, you can rewrite the entire equation in a certain way by kind of like doing the recurrence on paper, in closed form, realizing that it has a certain structure of like a mathematical formula, and that mathematical formula can be rewritten in ways that you can compute using matrix multiplies without materializing the state in between the chunk. So I'm not going to go into the details, but that's kind of what the high level there is. In Mama 2, we came up with this more general framework called state space duality that basically has dualities between linear and quadratic forms. And so the linear form is like the recurrence, and the quadratic form is this like matrix multiply based thing that you can compute very efficiently using the matrix multiplies. Um, and yeah, so back to my point, like there's many, many types of recurrent models. I do think that there's some differences in expressivity. So for example, to give you my opinion, efficiency is the most important thing. I think the models on the Pareto frontier of efficiency to expressivity are probably Mamba 2 and gated delta net right now. So Mamba 2 is going to be a much faster, a very, very fast recurrence, probably the fastest one of these modern models. Um, but it's slightly less expressive. And then gated delta net would be somewhat slower and somewhat more expressive. So depending on your needs, you get this trade-off. But all of them have this different trade-off compared to attention. So let me say a little bit about that with the time we have left. Um, so I'm gonna skip this. And so I showed the slide earlier that gave you the high-level differences between transformers and linear models. So um, transformers have to look at every past token and it becomes quadratic. Linear models compress their entire history and it becomes linear. Analogy that I like to use a lot is that um, I think of transformers like a database. Transformers basically, as you see more data, they have to cache all your data. Um, and so it's basically storing token level representations of your data into this like database like object. Um, and this and so it gets this very like fine-grained control over its history. It can always kind of like look back, when you're doing these pairwise comparisons, what you're doing is you're basically looking back into every past token and you're basically looking into your database and able to remember every single token exactly. And so you get very, very good recall and very fine-grained retrieval and these sort of fine-grained manipulations. On the other hand, SSMs are lossy and they're like a brain. They are like brains, are basically like um, coarse-grained objects with technically finite size, even though it's finite but very large, but still finite. Your history is not remembered exactly normally, right? Brains are very bad at doing things like exact retrieval, memorizing exact strings of digits or dictionaries or whatnot. Um, but they have different computational characteristics that make brains very powerful. And SSMs versus transformers have kind of a similar type of trade-off. So kind of I think of SSMs as basically the de facto model that is stateful and compressive. It's very good in any sort of interactive online setting where data is streaming. It's very efficient, and there's more subtle advantages too due to this compression. But it is bad at fine-grained recall and retrieval. Things like, needle and haystack, associative recall, and so on. And these trade-offs go hand in hand, and they're kind of, the same trade-offs that brains have. Brains are always on, very fast, real-time, online, bad at retrieval. Um, I'll briefly mention that, another point of human intelligence is that um, it kind of combines this brain-like mechanism with this scratchpad-like mechanism. Like our intelligence is heavily bolstered by using external tools like scratchpads, databases, dictionaries, Wikipedia, references, right? And so if you kind of think of external databases as transformer and the core processing unit as the brain, um, then this suggests that using hybrid models should have complementary effects. And these are some older ones, actually. Nowadays, hopefully you've heard of some of the more modern models like um, Quen, Kimi, NVIDIA's Nemotron. They're all moving toward hybrid models. A lot of them have found that in older times, people found that a 10-to-1 ratio of SSM to attention seemed optimal. Nowadays, people are using more like 3-to-1, 4-to-1, but it's still predominantly SSM. And it's kind of interesting how it tracks the analogy that using this analogy, you would think that intelligence is mostly the brain augmented by a scratch pad. And similarly, modern hybrid models are mostly linear models augmented by attention. And I think more generally, we are seeing evidence where the compressive aspects of linear models like SSMs are not like they used to be considered kind of like a problem. Like, oh, your state is not large enough. How can it be large enough to, remember all the data and process all the data? But actually, I think that compression can be viewed as a feature, right? Like I think compression is fundamental to intelligence. Intelligence requires you to take a big stream of data and compress it down to abstractions. And that maybe by having a smaller state, um, these sort of models are forced to learn better abstractions. Um, yeah, so okay, so for the sake of time, I think I'll just make one more final point and I'll go kind of fast. Um, so one of the main points I make is when talking about the trade-offs between these models is like um, these models actually do have subtle trade-offs. So there's this kind of a conception nowadays that transformers are the most powerful model around. If you can afford it, you should always just throw your data at a transformer, no matter what setting you're in. Um, and I think that there's truth to this. So transformers are extremely powerful. Don't think of me as like a like a transformer hater. Actually, like I think attention is amazing, a very critical primitive for modern machine learning. It's just that we need to understand the nuances behind it better than we currently do, um, and there's much more fine-grained lenses with which to understand these. So the reality is that you can't just throw your data at a transformer. Attention is effective when your data has already been compressed to good levels of abstraction. What does this mean? Let me unpack this a little bit. But let me actually first talk about empirically how do people use transformers. So, they're used everywhere. They're used in language. They're used in vision. If you look at how they're used in vision, what you do is you typically first um, take your data and you convert it into these more discrete tokens. So even if your data is an image and it comes in pixel form, you first convert it into like patches or tokens, which is a form of encoding, and then you feed that into your transformer. Um, in text, there's this famous step called tokenization. You don't operate over your raw characters. You first convert them into like these coarser chunks that are closer to words and other coarser chunks, right? That we call tokens, and then you feed this into your transformer. Um, Tokenization is known to be problematic. It's actually much more problematic than people even think it is. But there's some stuff I can't go into detail of. But like Andre Karpathy, for example, is a famous hater of tokenization and has written blog posts on all of these edge cases. And people are okay with tokenization because it just works. But I think the spirit of deep learning and AI is that we should be learning how to do things end to end. We should learn tokenization from data instead of manually engineering this. Um, But it's very interesting what happens when you do language modeling without tokenization. So this is still language, just kind of on a different resolution of input data. And so what happens if you try to do language modeling at the character level, which was first done by this paper called Mamba Byte, showing the comparison. What happens is that SSMs are dramatically better than transformers. Um, so here's just showing some training curves um, with flop matched models, and the transformers in purple here and Mamba's in blue. So it is like this gap is huge, and if you look at the data efficiency gap, there's like a more than 2x data efficiency gap in that like it takes 2x less data to get to the same loss for Mamba versus the transformer. And similarly, if you actually double the flops of the baseline by giving it, so this require to match flops, this required like sliding window attention. If you give it global attention, it's doing way, way more flops. And then the performance is actually still a little bit worse, but doing way more compute. Um, and we see this for character level language modeling, which, again, like, this is interesting because it means that, like, that means that transformers are not strictly better for language modeling, which is what a lot of perception is. Because character level language modeling is still language modeling. It's just the data is being given at different resolution. And so the effective tokenization is very misunderstood, and the power of transformers versus other models is also very misunderstood. In other domains without tokenization, like other sort of like domains of sequences such as DNA, um, we also see similar effects where Mamba is much more data efficient or just much more powerful than transformers when your data is happening at these high resolution type of settings. And the reason is because so there are some heuristics for why attention makes sense, but the bottom line is that because of the nature of attention and how it caches the data, it means that it's most effective if your data is worth caching. It means attention is most effective if your tokens or your history, each element is at a abstraction level that is worth saving into a database. And so, for example, it is not really useful to save characters, right? Characters themselves don't have meaning. Why would you want to store a KV cache representation for every single character in your data? That's just kind of useless. And so that's kind of the core reason why attention is not really good when your data is at fine resolutions that don't have meaning. But when they're at coarse resolutions that do have meaning, such as word level tokens, which is what people usually use, attention becomes much more effective. And there's a gray area for lots of things like in vision, for example, patches can sometimes have meaning, they can sometimes not have meaning. And we see trade-offs where transformers have do really well in some ways on vision data, but are actually like much worse than SSMs in some ways. Um, and so it's kind of interesting to see that, the utility of these sort of compressive linear recurrent models, they can be used on all sorts of data. Um, and even though they were kind of developed for text, the applications that they've been used for actually only have text as a very small minority. So like 10% of applications have been for language, a ton have been for other modalities like audio, vision, and time series and other things. Because these modalities, I think, do not like, it's unclear. They don't have as clean semantics as language. And that makes attention much less clearly good for these modalities and things that compress the data like SSMs much better. Um, yeah, and so I think that's what one of the main things that I think is worth taking away. I'm going to skip this a case study, but this basically all goes to support the main thesis here, which is that attention is very effective, but it is most effective when your data has been compressed to a good level of abstraction that gives the input to the transformer or like the tokens fed into the transformer um, as much meaning as possible and coarse level meaning. Um, And yeah, so I think that this mythos that like Transformers are all you need is overblown, and I think we are now seeing a resurgence of architecture research where this is a meme I made, where traditionally like we have worked with like the gold standard model like a transformer, and we instead design the entire pipeline around it, from how you process and tokenize the data to all sorts of other things that we're actually doing that go hand in hand with transformers. Um, but instead we can try to move forward and keep improving architectures, um, with a lot of it is hard because you have to take a lot of factors into consideration from, the modeling perspective to the systems perspective and so on. But I think the philosophy that's ideal is to think of data as pure, do as little feature engineering as possible, and come up with the best models that can learn features automatically from the data. Um, and okay, I think I will end here for the sake of time. Um, so I think there's a few minutes for questions, but let's stop here.
Yeah, thanks, Albert.